In this video, we continue the in-class investigation. In the previous video, we finished the first part. Okay, we established 3 limit expression. Now let's look at the geometry question. Okay, geometry question. Now the result for the limit of sin x over x can be also determined using geometry. Okay, so in the second part, we just re-find the derivative of, we just re-look at the limit of sin x over x. Okay, sin x over x, the limit of sin x over x as x approaches 0 can also be determined using geometry. The diagram shows a sector of a circle OAC. Okay, so this is a circle, OAC is a sector. OA equal to OC. Central angle is x radian. Triangle OAD is right angle triangle because AD is a tangent. Okay, AD is a tangent perpendicular to OA. Okay, so given that the area of the triangle OAC is half r squared x, okay, triangle OAC is half r squared at sin x. The area of the sector is half r squared x. Okay, so this is using the circular geometry formula of the area of the sector. Now, find the area of the triangle OAD in terms of r and x. Now, OAD is a right triangle, right? And we know that OA is perpendicular to AD. So the area of the triangle OAD, that area can be equal to half times base times height. So it's OA times OD. Sorry, OA times AD. Okay, OA times AD. Now, OA we know is R, but how about AD? And then you can realize this AD is opposite to X, right? So this AD is like opposite, and this R is adjacent, right? So AD over OA is equal to the tangent X. Okay, AD over OA is tangent X because it's opposite over adjacent. Okay, so the AD is equal to OA times tangent X, which is R times tangent X. Okay, because AD over the radius equals tangent X. So AD equals R times tangent X, which is half R squared tangent X. Okay, so now we managed to get the area of the triangle OAD in terms of R and X. Is this equal to half R squared tangent X? Okay, what is the use of this? Yeah. Now, clearly the area of triangle OAC is less than the area of the sector OAC, and then less than the area of triangle OAD, right? Okay, you can see the difference, What is the other angle as well? Okay. So OAC is like this part. Okay, smaller than the sector. Sector is getting bigger. And then smaller than the area of the triangle OAD, even bigger. Yeah, you can also see from here. Okay, I use highlighter this time. So the small triangle OAC, and then smaller than the sector. Okay, you can see the green sector cover the yellow triangle OAC. And then for OAD, is bigger than the sector, also bigger than the triangle OAC. Okay, so that's why obviously the triangle OAC less than the area of sector OAC, less than the area of triangle OAD. And if you remember their area, if you remember their area expression, this one. This one. This one. And then we can simply cancel half r squared. That's why we can get the conclusion that sin x less than x less than tangent x in this case. And then what happens next is, okay, now I'm going to divide this all by sin x. Yeah, so sin x over sin x less than x over sin x less than tangent x over sin x. Okay, please take note. Our x is in between 0 and 90 degrees. Okay, that's why the sin x is positive. Okay, our sin x is positive because x is an acute angle. That's why the direction of the inequality doesn't change. Okay, sin x divided by sin x is still positive. Okay, so that is why sin x over sin x is 1 less than x over sin x less than, okay, this one. Now tangent x is sin x over cosine x. So this sin x over cosine x now divided by sin x, which is sin x over cosine x multiplied by 1 over sin x. You divide it by sin x means you multiply by 1 over sin x. So it's equal to 1 over cosine x. Okay, so now we show that 1 less than x over sin x less than 1 over cosine x. And this conclusion is derived from the previous one, sin x less than tangent x. Yeah. Okay, now after that, let us take the reciprocal. Okay, let us take the reciprocal. So 1 over 1 bigger than 1 over x over sin x bigger than 1 over sin x. Okay, this is like if you have numbers 3 less than 4 less than 5, 3 less than 5 less than 7, let's say, yeah. When you take reciprocal, 1 over 3 bigger than 1 over 5 bigger than 1 over 7. Okay, so here also, if 1 less than x over sin x less than 1 over cosine x, when you take reciprocal, less than become more than. Okay, so we have 1 bigger than sin x over x bigger than cosine x. So as we take the limit of cosine x as x go to 0 should be less than the limit of sin x over x less than the limit of 1. Okay, now we know that the limit of cosine x as x goes to 0 is equal to 1. Okay, is established in the first part of our investigation. The limit of 1 is always equal to 1 because it's a constant function. Okay, limit of 1 doesn't change, it's just 1. Now, sin x over x is in between these two. Okay, if this one, the limit of cosine x is 1, if this one also approach 1, then this one have no other way to go. It has to be equal to 1. Now this is called sandwich theory. Okay, that means a function lies between the other two functions, and the other two functions both approaching the same limit. Then the one in the middle also approaches limit. Now that's why we prove the limit of sin x over x equals 1. Okay, so in the part 2, we just reprove that the limit of sin x over x equals 1. In the part 3, we try to establish the limit of 1 minus cosine x over x. And we'll do that through a few steps. The first step is we're going to rewrite 1 minus cosine x over x as sin squared x over x times 1 plus cosine x. And here is how we do it. Now this one I will multiply by 1 plus cosine x over itself. So on the top, I multiply 1 plus cosine x. At the bottom, I also multiply 1 plus cosine x. The top equals 1 minus cosine squared x. The bottom is x 1 plus cosine x. Because sine squared x plus cosine squared x equals 1. So this 1 minus cosine squared gives us sine squared. And that's why the limit of 1 minus cosine x over x equal to the limit of sine squared x over x times 1 plus cosine x, because they're the same function. Okay. So if that's the case, right, now you hence let's find the limit of 1 minus cosine x over x. Okay, now how are we going to do this? Now let's play a trick. Okay, let's see. Now from here, what we can get is equal to the limit of this times this. Okay, because sine squared x can be written as sin x times sin x. X times 1 plus cosine x can be written as x times 1 plus cosine x. Okay, so the top sine squared x, I separate it into two functions. Now, the limit of a product, unlike the differentiation, the limit of the product is simply the product of two limits. We learned that in differentiation, you cannot do like this. In differentiation, we have a product rule to follow. The good thing of limit is just bring in the limit sign. Okay, so now it becomes the limit of sin x over x times the limit of sin x over 1 plus cosine x. So for the first one, for this one, we know it's just equal to 1. Okay, for second one, we can simply sub 0 into it. And we know sin 0 is 0, cosine 0 is 1, so 0 over 2, which is 0. Now at this stage, you cannot substitute. If you substitute 0 inside, you get 0 over 0. But for sin x over 1 plus cosine x, you put 0 in, no problem, because the bottom, the denominator, is non-zero. Okay, so in doing this way, we can prove the limit of 1 minus cosine x over x is equal to 0. Okay, so in the investigation, 2, part 1 until part 3, once again, we establish those limit expression. The limit of 1 minus cosine x over x is 0. The limit of sine x over x equal to 1. Now, why do we need to keep proving these two limit expression? Because they are very important in finding the derivative of sine and cosine. Okay, which we'll talk about that in the next video.